drinking, you're driving.
Yes.
Excellent.
So we will be talking about biology of sand filters and the problem that developed with biofilm. We'll talk about disinfection byproducts, very important one.
Yes, and here especially we talk about trichloramines, THMs, mainly chloroform, and chlorates. That maybe some of you are not aware. That will be a really good session. Okay, and finally we have Q&A. But in the beginning, small change. Next slide. Small change, Philip?
Yes. So instead of using the Q&A, this time, please only use the chat function. When you do so, go into the chat box, click to all panelists, and click all panelists and attendees. This will allow us to pull up your questions at the end of the session, and everybody can see it and read them.
Yes, because that's what we have seen. You know, we get the questions, we see them, then we read them, we try to answer them in the same minute. That's a little bit stressy for us and not comfortable for you. We made it a change. We use just the chat function. Huh?
Okay, great. And as always, right, you have 7 days to watch the session from last time, then it will be replaced with the new one. And on our website as well, you can download the program and you can download the PDF with the PowerPoint slides.
Yeah, so nothing wrong, nothing new in this. Short summary of last session, session number 3, in 3 simple steps.
Number 1, we were talking about pipe dimensioning. What is important? Speed, length, and turbulence are the key factors. Speed being the most important one. If you slow the speed down by a factor of 2, your pressure drop in the pipe will be reduced by a factor of 4.
Exactly.
Step number 2.
Step number 2, use the magic ruler. It's really magic. And remember, you know, if you control the speed, you control the resistance. And with this, the energy consumption. Suction side speed 1 to 1.5 meters per second. Pipe velocity is quite fast. Pressure side 1.5 to 2. You can go lower, you should not go higher.
Right. And if you attend all 10 sessions, you will get one with a certificate.
Yes, exactly.
So
and
step number 3,
use this eco mode for overflow pools. You can save so much of energy. You can make it better. And we are here, you know, also to save energy. We are a green company, and we want to make it best for the environment. On top, you can save a lot of money with it. You can for your customers, and you can make your balance tank smaller. If you backwash directly from your pool, you know, it's better backwash, it's cleaner, it's just better.
So, who wants to talk about this? The 4.
You tell me.
4 elements of pool water treatment. Number 1, the importance of pool hydraulics. We covered this in our first 3 sessions in detail.
Yeah. Remember how much of turnover rate we have. We talked about the pipe dimensioning in the last one. And also in step number 2, we talked about filtration velocity, the importance of enough backwash speed, velocity, backwash velocity. So you have to take over, or I take a little bit of water.
Yeah, we're good. Then we talked about shortly about fresh water, and now we're moving into disinfection.
And with disinfection, also disinfection byproducts. And really, you know, we want to have the best water, the safest water. This is the mission from Howard, you know, to avoid toxic byproducts. And this is exactly what we will talk today, which is, of course, a function of part 1 and part 2.
Yep, exactly. So let's start talking about biology in sand filters and what this means, huh?
Sure. Can I have the...
Yes.
This is my favorite.
This is your favorite one. You can have it.
So today it's really about biology, so biology session. And by the way, if I may add this, you know, what really makes us different to the rest of the industry is Howard, because he's a biologist, marine biologist, and he was the first who really brought this biology thinking and this biology knowledge into our pool industry. So let's start with this. You know, you have in each pool you have heterotroph bacteria. Heterotroph bacteria, again, these are bacteria who are feeding from organics and produce something inorganics. These are bacteria who can grow very quickly. You know, if they have enough food, nice temperatures, 30 degrees, they double every 30 minutes. And the first one, the pioneers, are the Pseudomonas. So they are swimming in the water. They're very sensitive if they are planktonic, if they are alone to chlorine. You know, they're very easily killed. You know, but out of billions of these bacteria, always few of them will survive even high chlorine concentration, will find within seconds a surface that is in contact with the water. I go back and one back and will attach to this surface. And the moment it attaches to this surface, it will secrete a slime, a mucus, a slime, to protect them against chlorine oxidation or any other oxidation. They want to survive like we want to survive. You know, that's their mechanism to survive. And then they are covered, and then they double, they grow, they double, they grow, and this slimy mass, this bacteria in this slimy mass that we call a biofilm, becomes thicker and more stable. Mm. And by time, you know, it gets really very resistance against chlorine. You know, even high chlorine concentration, up to 50 ppm, cannot fully oxidize this biofilm, because chlorine has to oxidize from outside to inside. Chlorine cannot penetrate the biofilm and kill the bacteria inside. It really has to eat through. And by this process, obviously, it loses concentration. You know, and if you go, of course, with 50 ppm of chlorine in such a biophile system, you will remove 99.9999% of the biofilm, but you will always have, out of 1 billion, you will always have few that will survive. You know, the superbugs, the very strong bugs, the James Bonds of them, and they have then all the food available and all the nutrients available, and then they can grow and double again. So that's really about. Nadine, can you, yeah, please play this? You really see this well. You know, here, let's say this is a wall or this is a sand grain. You know, they stick to the surface. As you can see, they stick, I can look at this video. And then they build up the biofilm, and you see how they are protected. Again, I think it's a really nice animation. I think we have it from Patrick from Spain, from PS Pools. Thanks a lot, Patrick. So it really shows this very good. Or was it from Thomas?
I think I'm not sure. This was from the Daisy video, maybe. But
I think we've stolen it, honestly. You know, our community is great. You know, these guys, they are doing these things.
We share.
Yeah, yeah, nearly everything.
Yep.
You know? Okay. So this biofilm, you know, develops on each surface that's in contact with the water. And of course, there can be your pool, the floor, the walls, there can be your piping, but definitely it will be also your filter media, you know, because one more. 1 cubic meter of sand, you know, has a surface of 3,000 square meters. Oh, it's a really big surface. And, you know, within days, you know, each and every grain will be colonized from these heterotrough bacteria, and that will look like this. You would not see it. You only see it under a very special electron microscope, but it goes really quickly. And yeah. Maybe to you.
Okay, I handle this. So everyone who knows Dominic knows that you know, should not always believe 100% he says, even though I have to tell you most of the time he's right. So I double checked his statement. He said, you know, 90% of the pool surface is, you know, in the filter. So I did a short calculation here, right? If you look at this, we say we have a pool volume, 480 meter cubes, turnover time of 4 hours. We have flow rate of 120 meter cubes per hour. Let's say we have 2 filters, 1600 diameter. This gives us a filtration surface of 4 square meter times the bed depth. We're assuming 1.25 meters. So we have a total sand volume of 5 meter cubes. This times the 3,000 square meter of surface, and that's a fact, gives us 15,000 square meters. The pool surface, if we calculate the surface of the pool, the walls and the bottom of a pool of that size, here we will get a total pool surface of 425 square meters. So I guess you were right.
You missed the pipe.
I missed the pipe. Okay,
maybe
so
another
how much is the
100.
pipe?
That's maybe another one.
If that, right? So
ignorable.
we're in this particular case, we're way above that. So 90% of the surface is an accurate statement.
You know, in residential pools, maybe it's less, maybe it's 80, but usually around 90. If you solve the problem in the sand filter, you solve the problem to 80 or 90%.
So you were right again.
Yeah, that's my problem.
I hate to say that.
Call me genius, boy.
I hate to say that.
Call me genius, boy. Okay, and what's the problem with this biofilm? I mean, why do we mess around with this biofilm?
Yeah. So there are a number of problems. One of the first one we want to mention is the channeling and coagulation of sand. Biofilm leads to clumping and channeling of the bed. The sand grains will start to stick together because of the biofilm. And over time, you will start to see channels to go through the bed. This means that bacterial flocks will be able to get discharged back in the pool. This means the turbidity in your pool will increase over time. Your chlorine consumption will go up over time, and you're becoming a very unreliable and unstable filtration.
Okay, question, Philip. Are these channels then always open? You know, are they fixed? And
they're not always open. They have a tendency to close and then maybe open up for just seconds.
Yeah, usually
or minutes and then close again, right?
Maybe just 5 minutes a day, you know. But in this time, you know, your water doesn't not go through your filter, you know, in a slow velocity, 30 or 20 or 50 meters per hour. You know, you have highway where it passes through, really unfiltered. And this is where your pool is not anymore safe. You know, this turbidity will tell you now you are in risk, because these bacteria flux, they are quite well protected. They are not planktonic. These are not individual bacteria. They are protected in bacterial flux. And also, for example, crypto, we will talk about this in session number 9, especially in the UK, you know, you get them through. And then you have a chance to get crypto. So this is in a way not.
So this is what biofilm looks like.
Yes,
you see it here forming. This is still the clean sand here. More or less clean,
You just feel, you know, it's clumping together, and everybody of you guys who have changed sand, you know, you know this. Often it's also smelling a little bit, which comes, by the way, very often from autotroph bacteria. And maybe a last word to this, you know, autotroph bacteria, by the way, we have talked about heterotrophs, eating organics, producing inorganics. Autotrophs is just the opposite. You know, they are consuming inorganics and produce organics. They do not grow every 30 minutes. They double every 10 to 12 days. So they are a lot slower, a little bit like our people from Bern compared to us.
The government.
Yes, our government. Yeah, that's a good one. But, you know, when they move in, they produce the food for the heterotrophs and vice versa. So this is usually after 3 to 6 to 12 months, really, depending on the load, depending on the temperature, depending on the backwash regime. But this is when this biofilm becomes a lot more dynamic. And this is really when you start to get this clocking, this channeling. You know, everybody of you, you know, if you change the sand, you know, the first few weeks, it's working perfectly. It's working really good. You get the problem later on. This is because of the autotrophs. And really, you know, a lot of people, that was also new for me. It was hard for me to believe, okay, bacteria can grow on sand. Yes, it can. It can. Look, I can tell you this, in aquariums or in aquaculture, you know, very often we use fluidized sand beds to grow bacteria, you know, where you get the water from below to up. You know, you always fluidize the sand, the bed, to grow heterotroph bacteria on it, because they're eating organics. So this is what it's called biofiltration. And this is actually really great. It's needed in aquariums and in very often in aquaculture, but not in pools. In pools, we don't need that.
Absolutely not. So the consequences are, if you don't have biofilm in your filter, that means your grains are not clumping. You will have no channeling, and you will have a reliable filtration, right? So,
do you want to take your glasses? You look so intellectual.
Yeah, it's fine. I don't need them right now. That's
just
good.
look,
That's
you're
good.
a little bit behind. I'm
yes,
getting too
let's ramp it up. Okay, problem number 2 with biofilm in a sand filter.
Yeah, this is really, this is about pathogens. You know, I already mentioned it. You know, the first to build up the biofilm, these Pseudomonas. These are the pioneers. They build up the biofilm, and later on you have other microorganisms who move in. One of them is amoeba, and also Legionellas. You know, Legionellas can live in water or in biofilm, but not amoeba. Amoeba only can live in biofilm. So again, what's the problem with the biofilm? It's amoeba and Legionella. Let me explain you this. You know, Legionella live in water and in the biofilm, but they really grow in the biofilm. Why? In the biofilm, there are other bacteria who want to eat the Legionella, but they want to survive. So they go to amoeba and let them absorb, you know, like you can say, the amoeba is eating the Legionella, but they cannot digest it. You know, the Legionella has a mechanism that protects them from being digested. So it's, in a way, it's their home, their safety home. You know, they are absorbed by the amoeba, then they double in the amoeba, they grow in the amoeba until the amoeba is bursting, and then you have one shot, you have, I don't know, 100, 1,000 of Legionellas. Now, again, what has this to do with the biofilm? If you don't have Pseudomonas, so you have no biofilm, so you don't have Pseudomonas, then you don't have amoebas, and that means you don't have Legionellas. I make it a little bit black and white. It's not really like this. You have much less chance to get Legionellas because this growth mechanism is not anymore here. You got this? And still remember, you know, how quickly these heterotroph bacteria can grow, you know, in this biofilm. In this biofilm, you know, in general, in this biofilm, you have a full variety of microorganisms. You have bacteria, viruses, pathogens. So if you don't have this biofilm, you don't have all these problems.
Yeah. Okay. So problem number 3 with biofilm is the formation of trichloramines. Huh?
Yeah. You take it?
Yes.
Or I take it. I control it. You take it. Yeah. Good.
Okay. So let's start with what bathers, swimmers bring into the pool. We all bring an average of, 50 milliliters of pee. We bring in sweat. If you use a pool as an athlete, you sweat up to 1 liter actually. And
yeah. You can call us, and 80 milliliters of you can call us athletes. So we are above the average.
Maybe above the average, right?
Even if we are not training for 2 hours.
Yeah.
So anyway, you bring urine and sweat in, and the importance of this, it's not the same molecule, but they are pretty similar, because 80% of urine and of sweat is urea, which is organic. You see here, there is a carbon, and only about 10% is ammonia. And then you have creatine and amino acids. Let's forget about this. It's a small amount. 10% is ammonia, inorganic. 80% is urea. And why is this important? What has this to do with the biofilm? This urea, again, it's organic, is a food source for these heterotroph bacteria. They are eating it, and as a shit, if you want, or maybe that's the wrong word, they produce ammonia. It's not exactly right. This, the urea feeds the bacteria in the biofilm. The urea is converted by bacterial enzymes, the urease, to ammonia. That's the right word, but for me, the other ones works.
Yeah, I think we can all relate to it.
Okay.
Yep. And then the ammonia reacts with chlorine,
yes, and forms inorganic combined chlorine, which is mono, di, and trichloramine. That means if you have biofilm, let's say you have sand, you grow biofilm, then all your urea, again, I make it black and white, is converted into ammonia. Now you have 0 urea, 90 ammonia. And this reacts with chlorine to inorganic combined chlorine. So you see big part of your combined chlorine is inorganic. Other way around, if you have AFM, then you don't have a biofilm. Then your urea will stay urea. It will also react with chlorine and form organochloramine, chlorurea, which also is a combined chlorine. It will also give a DPT3 reading, but it's not toxic because it's absolutely not volatile. This is what we talk about this in session number 8. This is why we need in indoor pools if we want to be below 0.2 combined chlorine deactivated carbon. But let's come back to this. So again, we have, I repeat this because it's really a key one, urea, food source for heterotroph bacteria. It's converted into ammonia. Ammonia is then reacting with chlorine to form monochloramine, dichloramine, and trichloramine. And trichloramine is volatile. It gases out, you know, it has a Henry constant of 435, so it's very, very volatile. And the last one may be this. If you want to form from monochloramine, dichloramine, and trichloramine, you see this a little bit in this graph, you know, usually in the pH we are working in pools between 7 to 7.4, you mainly have monochloramine, a little bit of dichloramine, and nearly no trichloramine. Trichloramine formation really starts with pH below 6. Now, you may say, Philip, there
pool's never below that.
Yeah, we are not there. It's true. Your pool water not, but your filter, because the biofilm in your filter is acidic. You know, bacteria, they excrete an acid, and that makes the biofilm acidic. And the thicker, the more biofilm you have, the thicker it is, the more acidic it is. You know, it can be 5, can be even 4. And now for 1 or 2 minutes, you go with 30 meters per hour or 20 meters per hour, you go through your sand filter. And this is where you from monochloramine, dichloramine, and then trichloramine. And again, this is volatile and gases out. So as a summary, and then I give it back to you. I know I've talked too long. No biofilm means no trichloramine. Again, black and white. No biofilm means much less of trichloramine. And this is something that you can smell in each and every well-operated AFM installation. Philip, maybe you go on.
Yes, okay. So what's the problem with trichloramines, right? Because yes, you said they are gassing out, but what does that really mean? Trichloramines are very corrosive and they're very aggressive. When they gas out of the pool surface, which they do really easily, and as soon as the water is moved, they will gas out instantly. They will collect at the top of the ceiling, for example, and we all know pictures like these, they are responsible for corrosion.
Yeah. By the way, in the 1970s in Switzerland, a full roof in an public indoor pool came down and killed about 10 people in Uster. This is where the village where I was born in Zurich. Don't mention it. Okay, let's go on.
It's too close to Zurich, huh?
Yeah, it is.
Okay, okay. But the much bigger problem here is really the health effects it has. Because it gases out, it means bathers, swimmers are inhaling the trichloramines that gas out of the water. Inhaling them means that the trichloramine that enters the lungs is able to remove the protective layer that we all have in our lungs. And this leads to asthma, this leads to allergies, this leads to something that's called in the US a lifeguard lung disease for people who work in indoor pools. So we know trichloramines, these disinfection byproducts, but especially the trichloramine is toxic and it is harmful and bad.
Yeah. Maybe to trichloramine, it's really this what you're smelling, you know, because it's volatile. You see this here in the Henry constant, 435. The higher the number here is, the more volatile it is. You know, the easier it is for this gas to get out of the water. And, you know, if we come in an indoor pool, usually people say, oh, there is a lot, they smell and say, there is a lot of chlorine, and they think it's in the water. Now, if you come in an indoor pool and you smell the chlorine, it's just the trichloramine. It's not the chlorine in the water. If you want to smell the chlorine in the water, which would be, which would be here, the free chlorine, you know, the hypochlorite acid, you know, Henry constant below 0, you know, never will go out. You would have to put your nose into the water and breathe in, but that's not that comfortable. So it's really the trichloramine. You know, and maybe one word also, do these DPD measurements. You know, actually from a health point of view, we should measure trichloramine in the air, and you can do this, but it's a lot more complicated. You know, you have to take a filter, you have to take an air pump above 1 meter above the water surface, and then you pump for 1 hour the air through this filter, and then you analyze this filter. Now, this is too complicated for most people, and this is why we still use DPD method. DPD1 for free chlorine, DPD plus DPD3 gives DPD4, that's the total chlorine, and the difference is the combined chlorine. This is a good measurement. It just gives us a little bit an idea, you know. By the way, this measurement is older than you.
The DPD?
Yeah, it's from 1957.
You mean it's older than 35?
Yeah, you're really good in calculating. Yeah, no, it's fucking old.
Wow, okay.
Yeah, so maybe also something to change. By the way, if you want to measure once monochloramine, measure DPD1 for free chlorine, then add plus DPD2, and then you have this value will give you the monochloramine. And if you multiply this with 1.4, you more or less have mono, di, and trichloramine. Again, trichloramine is very volatile. If you move the water, it will gas this out. The beauty is your combined chlorine in the water goes down, but you just move the problem to the atmosphere, and where it's even worse. How are we in the timing?
Not good.
Okay,
yeah.
Let's go on.
Yeah.
Biofilm. You can have it, you know, in walls, channels, pipes, balance tanks, but we have seen this is small quantity. The main problem is in the filter. And if you solve the problem there, you have done it. You have done it. So
how can you eliminate or prevent the formation of biofilm? You have basically two ways, two good ways. One is the elimination through the use of chlorine dioxide. Chlorine dioxide will pass through the biofilm. It will penetrate it. Chlorine will not. This we will talk about in session 9. Or even better, prevent the formation of biofilm in the filter with the use of AFM, because AFM is 100% bioresistance, no biofilm. We'll talk about it in a week from today in session 5.
Very good. Philip, you're my friend, but you're telling shit. There is only one good way, and this is the prevention. You know, if you have biofilm, I agree with you. That was correct. You know, how to remove the biofilm. Chlorine dioxide, we talk about in session, but this is the chemotherapy. You know, this is when you already have cancer and you make therapy, chemotherapy. Yeah, do it good way. Go for AFM, bioresistant filter media, so you do not get cancer. That's the biological solution. Sorry to say. But I think it's a good analogy.
It's the biological solution.
Yes,
absolutely.
Absolutely. And now we come to chloroform. That's actually one of my favorite areas. You know, one back. You know, I said before, AFM does not promise that you have less of combined chlorine, of total combined chlorine. AFM is a promise that you will have less of inorganics. And maybe you say, Dominic, I don't give it's not my concern. It's not my concern. I think that was the right expression.
That's nice.
It's not my concern. I don't care. I mean, it's really less of inorganic. Let's say it's not important. Less of chlorine smell. That's in a way important. But about chloroform, I can promise you, using AFM in the right way, you will have 50% less of chloroform and other THMs. Let me explain this, or together. Shall I take that? Or?
Yeah, go ahead.
Okay.
I'll tell you if you're wrong.
Okay, I would love that. Here you see an organic compound. You know, there is carbon, usually long chain molecules surrounded with some other atoms, usually hydrogen, this H. This is an organic compound. Now we have chlorine, which breaks these double bonds. You know, they are like two hands, you know, both carbon give a hand and you break them. Or also with UV, you know, that can be the sun, that can be a UV system, especially the medium pressure UV system, will break up these double bonds that you see here with the blitz. What is a blitz? Flash, which will break this. And the smallest molecule that you will end up is a methane, which is 1 carbon, 4 hydrogen. This is a methane. This is the smallest compound. So what we do with this oxidation, we just split big molecules in smaller ones. And the smallest is a methane. Now, whenever a methane comes in contact with chlorine, you know, you replace one of these hydrogen, then two, and then three of these hydrogen. So you have here now 4 chlorine atoms, still 1 carbon, and 1 hydrogen. And this is chloroform. And chloroform is one of the THMs. It's one of the trihalomethane. It took me 20 years to understand really what trihalomethane means, and I'm very proud now. Since 10 years I know it, and this is why I want to share this big knowledge with you. Why is it called a trihalomethane? Because it's a methane where you have 3 halogens now on it. That can be chlorine, then it's a chloroform. That can be bromine, which is also a halogen, then it's bromoform. Or it could be iodine or fluorine. So for us, it's just the bromine and especially the chlorine, which is important. So chloroform is one of the THMs. And if we are talking about THMs, if you use chlorine, we will talk about chloroform. It's really about chloroform.
So chloroform, didn't they use that to put you out? Or like an anesthetic?
Yeah, huh? It was the first anesthetic.
Yeah.
And Queen Victoria I, you know, she got her first birth. She was the first who gave birth with chloroform. You know, before you had this, I mean, birth is always quite a painful job. But I learned, I have not my own experience. I mean, I was with it, but not really my own experience. But, you know, anything, you know, when they had to cut you off or whatever without anesthetic, the only solution you had to drink 2 bottles of whiskey, try to survive that, and then say, go on. But still, it was quite a painful thing. So anesthetics are, in a way, a good thing, but it does not make you smarter.
Like alcohol, huh? I guess.
Yes. It's
okay. It doesn't really make you smarter.
Yeah,
you only think you're smarter, but
yeah. But if you wake up, you have your headache, you feel it did not make you really smarter. So alcohol is not good for you, Philip.
Yes, Dad.
Also not for me, and also not chloroform.
Yeah.
Now it's really how can you reduce chloroform? Reduce the organic load. You know, put less. Shower more, bring more fresh water in, or take out more of organics, filter more out. Now, if they are out, they cannot react. This is really what you can do. And yeah, maybe again here, you know, same thing. It's volatile, less volatile than trichloramine. Henry Constance 185. It's not bars. This is wrong, but however. It goes in your lung, but here comes the difference. It will not just remove this layer from your lung, it will go through your lung in your bloodstream and then on your nerve system. And this is why it's a lot more dangerous. You don't see it, you don't smell it like trichloramine, but it's much more dangerous.
It's really bad for small kids, huh?
Yeah, that's the next slide. Yeah, maybe you.
Yeah. Great. Yeah. So I learned that, you know, kids younger than 2 years don't have a fully developed blood-brain barrier, which means these toxins can basically pass through directly. Huh?
Yeah.
So very dangerous for small kids.
Yeah, that's for babies below 2 years, but also for pregnant women.
Yeah.
So I guess you're not in risk, you're not pregnant, but that's really not good. So really then with babies, or if you're pregnant, really just use very safe pools, you know, with THM levels below 20, which means daisy.
Okay. So you mentioned,
very simple.
You mentioned that the amount of organic pollution, you can go to the next one, is very important, right?
Yes, exactly.
And
that's really important.
There is a way to measure this, huh?
Yeah, there are 2 ways, K-4 or TOC. K-4, maybe you explain. It's the same. It measures how much, it measures the oxidability of the water. That means how much of organics. Maybe you explain the K-4, you know, that you understand if you see these ones. Yeah,
so K-4 is an oxidant that you add to the water. And while it is, you know, oxidizing the organics, it gives you a measurement of, you know, how much organics it is oxidizing. So it gives you an indication, or actually a very precise measurement of what the organic contamination or the amount of organics in the water are.
To be honest, I'm not 100% sure that comes from flow. I even do not know if he's 100% sure, but I think this is your water sample. Then you put in some color,
Changes,
and then that's purple, and then you give in K-4 until it changes the color.
Yeah.
You have to take the microphone, otherwise we can't hear you. However, the more consumption of this very strong oxidants of this potassium permanganate, the bigger is the organic load. And we do not want to have this organic load because, and this you see here below, organics are a food source for every heterotrophic microorganisms. They increase chlorine consumption, but really they increase also this formation of trilomethanes, chloroforms, and all the other ones. So, Philip, what's the solution?
So, if you want to reduce your organic, well, if you want to reduce the formation of that, then you need to reduce the organic load. How can you do this? Number one.
Yeah, if you want to reduce the organic loads, you can shower or bring in fresh water. But if you have them already in, the best way to take it out is?
To use AFM.
To AFM. We filter at least 50% better, twice as good as sand. That means we have half of the organics in the water. And with this, you have half of trilomethanes.
Yep.
K-4 or TOC, both are, again, it's a value for the organic load. TOC multiplied with 1.5 is K-4, more or less. So it's just a different measurements, but both tells the same. They go hand in hand with THMs.
Yes.
So if you just take more out, filter them out, and backwash it. And if you want to increase this for another step,
use a coagulant or flocculant, for example, our APF, which we will cover in session number 6.
Yeah, I really would recommend you to join these 2 sessions and to use this because it's the very best. Let me tell you one small story. That was an unplanned one, but I'm not sure if you have the time, but I will. Maybe on the call is Stavor, my friend from Croatia. He brought me to a hotel pool, where they changed to AFM and they had really good value. K-4 was brilliant and was really good, and THMs were really good, below 20. Suddenly, 2 weeks after, he said, now THMs are on 400. And I said, oh shit, this is not good. So where is K-4? Yeah, it's still on the same or even below. I said, this is not possible. And Dover, he was nervous. He was a little bit new he's a really good expert in water treatment, but also in a way a little bit new in the pool thing. And at that time, he didn't trust me. So I went on my way from Serbia, I went to Croatia and we visited it. And they had, again, the same result. So I went to this director of the hotel and said, sorry, but your analysis is wrong. And believe me, this guy, he was not happy. He said, you're arrogant, can't be. I said, go for another lab, make another check, and then let's discuss again. And that's what they did, and I was right. And I love to be right. So one thing is clear, you can't have high THM levels with a low organic load. If you have a low K-4, it's impossible that you have high THMs. THMs needs 2 things. It needs chlorine that we have to use, and it needs organics. So the more you remove, the less you have. How are we in timing? Not great. Okay, let's talk about chlorates. My chlorates maybe in most of the countries is not such an issue, but it's definitely an issue in Switzerland. It's definitely an issue in Germany and in Austria. And it will become an issue in other countries, because Germany goes first, let's say, and then all the rest in Europe will follow. So good chance for the UK after the Brexit, you will not be touched by this, but still interesting to see. Let me quickly explain what is chlorate. Chlorine can have different oxidation states. It can be CLM minus, that's the first oxidation state. It can be called chloride. It can be hypochlorite, so sodium hypochlorite or calcium hypochlorite, where you have ClO minus, this is 1 positive. If this is in the water, exposed to temperature, exposed to sun, and over the time, this will be decomposition. Do you say decomposition?
Yeah.
Decompose
Yeah.
the right word, to chloride, which is this ClO2, and then to chlorate, and later on even to perchlorate. But we are interested here now in this chlorate, in this ClO3. So we are interested in this because this is not so good. And why is it not so good?
Well, why are chlorates not good for us? Short story, let's start with hemoglobin. Hemoglobin is a molecule in your red blood cell. And it contains iron Fe2+, and it is responsible for the transport of oxygen in your blood to your cells. And in order to do that, the Fe2 iron in the hemoglobin binds the oxygen and moves it. Chlorate now, if exposed to chlorate will oxidize the Fe2+ in the hemoglobin and convert it into Fe3+. And this takes the hemoglobin, the possibility to bind oxygen and move it to your cell. So as a consequence, you lose your possibility to provide your body with oxygen. And this leads to, headache. It leads to dizziness, even at only 20%. This process starts to happen. This is why we have these limits in Switzerland, in Germany, because this is really starting to become a concern.
So there is not enough of oxygen. You get a headache. It's
Exactly.
a bit like if you wear masks, right?
Exactly.
Yeah. Okay.
Yeah.
I don't
That's
like
what you
masks.
get.
I don't like hemoglobin.
Yeah.
Okay, so
Yeah.
it's not good, really. And this is really, here you see the values. In Germany, they should be below 30. In Switzerland, we are more sportive in this category. We should be below 10 milligram per liter. By the way, also Germany wanted to go to 10, but then the food industry became very nervous and then said, okay, let's go back. So where is it formed? Mainly in sodium hypochlorite. It's really in this liquid chlorine, mainly in the sodium hypochlorite. Let me explain you briefly this. Here, this clear line is the curve. Now first, here this I-axis is milligram per liter. This is the free chlorine of sodium hypochlorite. So if it's fresh from production, you have, let's say, 120 milligrams per liter of active chlorine in the sodium hypochlorite. And here, 1, 2, 3, 4, these are the months. And here you have different curves. Here you see curves at 7 degrees, if you store sodium hypochlorite at 7 degrees, and you have a curve here where you store it at 36 degrees. What we see, if you store it at 7 degrees, your sodium hypochlorite loses in 4 months 10%. If you store it at 36 degrees, it loses in one month more than 50% of the concentration. In 1 month, more than 50% the concentration. That means if you dose now here, at that point, your sodium hypochlorite, you will have to dose double the amount than if you use a very fresh one. Now we move to these lines, to the gestrichelte Linie. What is gestrichelte? Dotted line. Same thing. Here, the blue line is if you store it cold. Here, if you store it at 36 degrees. This is the concentration of chlorates in sodium hypochlorite. There is a certain chlorates concentration from the beginning. It's roughly 20 milligrams per liter, now not of water, of sodium hypochlorite. If you store it in this warm, not good conditions, after 1 month, you don't have 20, you have 40. That means you have double. So now, if you store it and this suboptimal conditions, you will have to double the amount, and what you're dosing has double the amount of chlorates. This is why you have a factor of 4. This is what you see here. Your chlorate goes up. So it's really a problem with this. It's much less a problem if you use cal-hypo of chlorine gas. Let me also explain this to you. This graph comes from, that was an article in Beta Review not beta review, yeah, the German reports, you know, where the team makes a lot of analysis. Here, what they tested is sodium hypochlorite in solution, so liquid sodium hypochlorite and sodium hypochlorite, you know, from brine electrolysis, and each of these is a pool. Each of them is a pool. And then you have blue chlorine gas, and light blue you have calcium hypochlorite. Now, each of them was a pool which they tested, or they made different tests on different pools. So what we see, to be in the limit of Germany, some of them with sodium hypochlorite haven't done it. Probably because it was stored too long, but even with the sodium hypochlorite from brine electrolysis, they haven't done it. We also see that the chlorine gas and cal hypo worked a lot better. All of them have passed the DIN limit of 30. Some of them have not passed the DIN limit of the Swiss limit of the 10. So what does this mean? It's a lot. The problem is really sodium hypochlorite, especially if it's stored on the warm condition. If it's stored long, then you have this degradation. This is not good. You have much less problem with cal hypo and chlorine gas. You would have the same problem with cal hypo, you know, or why is this? You know, because as long as the cal hypo is a powder, it's not a problem. It will not degrade. But the moment where it's mixed into the water, it starts to degrade. So if you dose the cal hypo through a granidos, for example, from Werner dosier technique, you know, where you have up the powder, and when you need chlorine, you mix this with this mixer into the water, then you will not have a problem because you mix it in. It cannot be in the water and degrade. If you would take the cal hypo 1 kilogram in 100 liter of water, or 2 kilogram in 100 liter of water, because that's more or less the max that you can go to, and store it and dose it, that would be
it will
same
break
problem.
down. Huh?
Yeah. So long story short, problem is really with sodium hypochlorite, much less problem with cal hypo and chlorine gas.
And then, of course, with the Dryden aqua generator or DHN, chlorates will stay below 1 milligrams per liter. Huh?
We have not seen one. We have not seen one case where we were more than 1 milligram per liter. This is just the perfect solution.
Okay, so
you want to ask me why?
Tell us.
I don't know. Honestly, I don't know. I know it's the case, but I do not know. I have some ideas why it could be, but even not important. Let's go to.
Let's summarize. So, yes, summarize the solutions to reduce chlorate concentrations. Number one is add more fresh water. Dilution is the solution, right?
Yeah, but not a good solution.
Not a good one.
Sodium hypochlorite, store it cold and fresh. But, you know, in reality, you know, indoor pools, you have it in your technical room. Temperature is 30 degrees, sometimes 35. You're always sweating. So and the people say, yeah, bring me a full pallet because then I pay less. That's really the problem where you get in. Really good is
a daisy, because you reduce the oxidation demand of water.
Yeah, by 80%.
Yeah.
And that makes a huge difference. You know, for instance, a friend of mine called me in Switzerland, you know, they have with cal hypo chlorates above 20. And it's a DE filter, and he will not change the DE filter, but he said, I told him, okay, use ACO, so your chlorine demand will go dramatically down. Probably he will not get to 10, but lower than what he has. And then finally use cal hypo, and the very best would be the DHN. Now, let me quickly explain you this on a example. Here you see, this is in Switzerland. It's a very old therapy pool. You know, you see it's even still with skimmers. So it's really old, you know, 2 suction line, you know, 50 millimeter from the main frame and 63 millimeter from the skimmers, and 1 return line in the 2-inch. It is a very old therapy pool, how you built them 30 years ago. But it's very well used, you know, they have 33 degrees, they have 50 to 80 bases, they have handicapped swimming, they have baby swimming. And, you know, they renovated it 3 years ago because the Swiss government started to test also these pools, which were not tested before. And I do not know, you know, where the combined chlorine or the THM or the chlorates were before they did the change, but they were sky high. I'm sure, you know, they were, I don't know, more than 1 milligram per liter of combined chlorine, probably THMs 300, 400, sky high. This is how it looked like. You know, they had, for many years, they had here just a nice Sculplos filter, FA15, 640 diameter with sand. They had a pool manager, pH redox. It was never controlled. Water was clear, people could swim. Most of them survived, so all good. But then, yeah, then they came with the regulations. And here, this is Nicole Greinicher from Greinicher Schwimmbadtechnik. It's really a lady, one of my girlfriends, which I admire. She's great. She's really very technical. You can learn a lot from him. But she said, Dominic, I only can put in, she asked me, Dominic, what do I need? I said, you need 3 filters. You know, because the door is only 900. So I said, go for 3 800 millimeter filters. He said, okay, I don't have space, but even I don't have more piping. You know, I don't have 1 2-inch return line. So I cannot use 3 filters. Okay, let's try it. So she put in 840 with AFM, 1.1 meter or 1.1 meter of filter bed height, a DHN with free chlorine and redox and everything. Yeah, she did it the best she could, And then came the first result. You see, this was in July 2018, and the results were amazing. You know, I couldn't believe how good they were, but they were not good enough. You know, on the combined chlorine, we were just on the limit, 0.21 instead of 0.2. On the chlorate, we were great. We were not at 10, not at 30, we were below 1, 0.5, you know. This was my first, okay, it's interesting. And then the THMs were 72. This is in milligram. Usually you measure them in micrograms. So just multiply this with 1,000. There was 72 instead of 20. 20 is very sportive, you know. For instance, in Croatia, you need to be in 100, in Switzerland with 20. So, the health government said, okay, Nicole, you change or we close. And she asked me, Dominic, what can we do? And we worked together there, always like to be together with her and study it, and said, make a backwash. And I've seen, you know, it was very small bed expansion, while backwashing was still the old AFM with the bigger grading and the standard. And I said, Nicole, I think we have a problem because we have a CPM in. We didn't have the Flowys, but we had a CPM in. And this CPM, you know, if we want to backwash this filter of 840, surface is 0.5 square meter, at 50 meters per hour, you need 26 cubic meters per hour flow rate to backwash it. And if you go down to the CPM, the DN50, you see at this, you have a pressure loss of 400 millibar, 0.4 bar or 4 meters. So we made the decision, okay, Nicole, you take the CPM out, you dose the APF in the future in front of the pump here in the drainage screw, and you add a Flowys. So that means minus 400 millibar, plus 100 millibar. And this brought us to a new backwash curve. You know, before we had really a resistance in backwashing, and of course we only found it out by Flowys, of 40 meters. Yeah. And this was only 18 cubic meters per hour. Then we dropped by 400 by reducing the CPM. We increased by 100 millibar by installing the the Flowys. And now we are on 26. Yeah. So we are right. And look at the result here. That was 2 or 3 months later. It's amazing. You know, combined chlorine 0.06 can't be better. Of course, there is also 10 centimeters of activated carbon on it. Chlorates below 0.1 milligram per liter. I mean, unbelievable. And in the THM, we came from 70 and we are now at 18. So we just done it. And we are always a little bit on the limit, but it's always working. He will accept, you know, if you're once on 22 and then 18, but in average, we have to be below this. So this is really the learning, what you can do. This is not the message, ladies and gentlemen, go out to the limits. This is not the message. but it's important, you know, to control your flows, to do it properly. And the learning for the chlorates is DHN is the very best. Okay, session number 4. I give it, Commander, back to you. We're good in timing, by the way.
We are. Yeah. We're good. So let's summarize the key points of session number 4 in 3.
I think the key point is, if I have to control, we are good in timing. Oh, no.
Good. We have 1 minute left.
Yeah. Don't spoil it.
So first, no biofilm in the filter means less formation of harmful trichloramines. Learning number 2.
Less organics, better filtration, less THMs, less chloroforms. It really goes together. If you filter twice as much as organics, you have half of the THMs.
And learning number 3 is
best against chlorates, DHN. Second best, cal hypo.
No, you're wrong. The very best.
Oh yeah, sure. Sorry.
Okay, good. Okay, outlook for session number 5. In a week from today.
Yeah, we will honor a little bit our
founder,
Dr.
inventor of AFM.
You know,
yes.
He developed AFM, he developed AC, and ladies and gentlemen, he hasn't done it for us, you know, for the bull guys. He has done it for the dolphins. He wanted to give them a better life to avoid volatile disinfection byproducts. But we can profit now from this. And we will talk about this. Yeah. And if you go on the next slide,
this will be a great session.
Absolutely, yes. Will be a good. We will talk, you know, what we are doing in the activation, not all the secrets, but some of the secrets. We will tell you why AFM is such a game changer. Yeah. Again, we will cover quickly filtration, performance and backwash performance, what you should look, and the new layering 50-50. What is the optimal layering? So I think it will be really, really good. And I hope to see you again, same time, same place.